Okay, it's Brian, and I'm back for our second installment of physics classes in the time of social distancing, and this is our second day of talking about electromagnetic waves. And today we're particularly going to talk about this piece of the puzzle, that long wavelengths act like waves and short wavelengths act like particles, or more precisely, photons. And so this photon model is something we're going to take a look at today. And since I was going to be delivering this on Friday, it's Freddy Friday, so I would start the class with a Queen song. We are the champions. Okay, that's enough of that. Let's keep on moving, and let's start talking about class. But I first wanted to say I'm very thankful that I get a chance to have the job that I do, and I get a chance to share things I love about the world with such a cool, creative, wonderful group of people. I'm so sorry I can't see you folks in person right now, but I'm very glad that I still have the means to connect with you and that we had half a semester of good physics before things changed. Now, let's talk about the rainbow and what's beyond the rainbow. So here's a rainbow in the sky above the desert in southwestern Utah, and the light is broken up into a spectrum, and we see this spectrum of wavelengths, and it goes from red on the top to blue on the bottom. And that's our visible light rainbow. But that's only one tiny swath of the electromagnetic spectrum. And we're going to look at wavelengths that are much, much shorter than the blue and wavelengths that are much, much longer than the red today. We're going to be looking at the rainbow and everything beyond, because there's ever so much more to it. Now, the whole electromagnetic spectrum spans the range from radio waves, which we talked a little bit about last time, all the way up to gamma rays, which we'll talk about next week when we talk about nuclear physics. But today we're going to be particularly talking about modeling all these different things not as waves, but as photons, And I'm going to start by taking a look at this picture right here. Now, this is actually a gamma scan, and this was a gamma scan and looking at someone's bones, and you can see there's something clearly which is happening here, and probably a break or a tumor or something like that, lots of uptake of certain radioactive isotopes. We'll talk about how you make such images next week. But if you look at this picture, the person ingested a radioactive isotope, put their hand down on a piece of film, and each dot that you see in this picture represents one photon, one particle-like entity of the electromagnetic wave. And you can see, if you took actually a visible light photograph and you could blow it up and kind of like look at the details, you could see there are individual spots made by individual photons at the microscopic structure of such a picture. Because at a fundamental level, as it interacts with matter, electromagnetic waves tend to interact as photons. If you look at rod and cone cells in your eye, each one of these rod and cone cells interacts with a single photon of light. Single photon of light comes in and causes some sort of a transition in a visual pigment in a rod cell or a cone cell. And so it's a particle interaction, one photon of light interacting with one molecule of pigment inside a rod or a cone cell. Now, photons have energy that's determined by their frequency. And so this relationship right here is going to be a really important one for us. The energy of individual photons is just equal to this thing called Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. And Planck's constant is this number right here. It's in joules seconds, or in eV times seconds, because the electron volt, remember, is a unit of energy, and that's going to be a very important unit of energy for us in this particular. See that the energy of individual photons is inversely proportional to the wavelength. Given that of the course, here's a question for you. Looking on the previous slide, if we look at red light or blue light, red pen laser emits light of wavelength 670 nanometers. A blue pen laser emits light of wavelength 470 nanometers. Which has a higher photon energy, the red or the blue? I want you to think about that. And before you go on to the next slide, take a moment to cogitate the red or the blue and why. I'll be back. And of course, it's the blue. It's the blue because the photon energy is proportional to 1 over the wavelength. So if I have a big wavelength, if the wavelength increases, the photon energy goes down. So short wavelengths correspond to big energies. Long wavelengths correspond to small energies of the individual photons. And I'm going to show you a little video which brings up that point. So there's a video that I made as part of this sequence that talks about photon energies and different energies of photons. Are they able to make something happen or not? So at some point, take a look at that video. Now, reminder, this was our basic relationship for energies of photons, where I use Planck's constant as one of these two values, depending if I want to calculate the energy in electron volts or I want to calculate the energy in joules. We have a shorthand for calculating photon energies if I want to get the answer in electron volts, which is typically true. The energy of a photon in electron volts is just equal to 1240 divided by the wavelength in nanometers. And this 1240 right here is just a collection of constants and unit conversions that takes me from a wavelength in nanometers to an energy of photons in electron volts. And we'll use that regularly. So for instance, a real typical wavelength of light that we'd be looking at would be like 620. Red light, 620 nanometers, is kind of like towards the red end of the spectrum. The energy of those photons in electron volts would just be equal to 1240 divided by 620 nanometers, which is 2.0 electron volts. That's a typical scale of photon energy. So in the visible light spectrum, which runs from 400 to about 750 nanometers, we're going to be looking at energies that are in the single eV range. And that's why we use electron volts. It's a decent energy scale for this sort of thing. It takes something like a fraction of an electron volt to break a hydrogen bond. It takes a few electron volts to actually break a bond between the atoms in a water molecule. And so the electron volt scale is a reasonable scale for us. 1 eV is basically how much energy it takes to make something happen at an atomic level. And so we're going to use that as our preferred energy scale for the near term. Slide here. Oh, 4.7 electron volts, actually breaking bonds between atoms in a water molecule. Now, let's look at the whole electromagnetic spectrum and look at the energy of different wavelengths, frequencies. So if you have FM radio, the wavelength's about 3 meters. That corresponds to a frequency of 100 megahertz. The photon energy is a little itty-bitty 0.41 microelectron volts. So radio wave photons, not energetic enough to make something happen. Microwaves have shorter wavelengths. They're not really micro, but they're shorter than FM. 16 centimeters, typical wavelength. That corresponds to a photon energy of like 8 microelectron volts, still not very much. Now let's look at the visible light spectrum. Okay, right here in the middle of the visible light spectrum, and if we have to pick a wavelength that's right in the middle, I'm going to pick 500 nanometers. That's a frequency of 6 times 10 to the 14th hertz. Very high frequency. The energy, 2.5 electron volts, a typical energy for photons of visible light. If I go to longer wavelengths, red, I go smaller, down into the infrared, I get down to 1.2 electron volts here for the near infrared. That energy is getting low enough that it might not be able to make anything happen. It might not have high enough energy to excite molecules, might not get absorbed, it might just be reflected, or it might be passed straight on through. If we go to shorter wavelengths, if we go to the blue end of the spectrum, by the time we get to like the blue part, 3.1 electron volts. If I get up into the ultraviolet range of the spectrum, I'm getting up to a little bit over 3 electron volts. By the time I get there, that's enough energy that I might actually be able to start breaking bonds. And that's a crucial piece of the puzzle, because if I can start breaking bonds, oh, by the way, too, this isn't 3.4. Brian, you scamp, that should be 4.3 electron volts. That's 4.3 electron volts. If I get up to like 4.3 electron volts, look at a previous 0.3 electron volts, basically can make something happen at an atomic scale. I can break bonds. That's why these short wavelengths are damaging. That's why we wear sunscreen, to protect against ultraviolet, but we're not worried about being protected from the infrared. The energies are just too low to make stuff. Now, if I have long wavelengths, the waves tend to interact with matter like waves, like microwaves. It's the waves of the electric and the magnetic field that make things happen, as we saw in the last class. If I go to short wavelengths, they tend to look more like particles, so we're very much interested in the interaction of individual photons with atoms in some sort of material. And so I've got the ends of the spectrum. The short wavelength end, things look like particles. We would say they're particle-y. For the long wavelength ends, it's more wave-ish. They act more like waves. For visible light in the middle of the spectrum, it kind of depends. Does light act like a wave or a particle? It kind of depends on what you're asking it to do. If you're asking it to interact with a single molecule of a pigment, it's going to act like a particle. Does it absorb it or not? But there are cases where the wave nature is important. And we're going to see a whole lot of that stuff when we get to chapter 17, when we'll go back and do that stuff. Now, for long wavelength waves, like infrared, here's a parrot sitting in front of a heat lamp. The interactions are wave-ish. It just takes the molecules and vibrates them and feels warm. And so this parrot is just feeling a little bit of toastiness due to that wave. For short wavelengths, it's a very different story. For short wavelengths, they interact as particles. So here's a baby under a UV lamp, and I'm guessing that's because this baby was having jaundice. And individual photons of the ultraviolet come in and interact with pigments and interact with cells, and they kind of like will break up bilirubin and other sort of things that can help clear up jaundice. And it's the particle nature of those short wavelength photons that makes that happen. Now, here's a quick question, and we talked about this at the end of class last time. When you're talking on the cell phone, you are holding a microwave transmitter up to your head. How dangerous is that? Are you giving yourself brain cancer when you're talking on the phone? And the answer is no. But here's the thing. It's easy to convince people that these are dangerous because this is a microwave transmitter. It's emitting electromagnetic radiation, and radiation is a word that scares people. Radiation just means it radiates. It's kind of like the waves spread out in all directions. They are radiating. It is radiation. Some of it will go in your head. And people are particularly fond of doing scare tactics about children here because you want to keep your children safe. I mean, absolutely, you want to do that. So here's like a thing I found on the internet that was trying to convince me that this was really problematic. And it says, like, look, if you take a young child here using a cell phone, it penetrates their brain much more than for an adult. And the reason is there's a certain penetration depth. Any electromagnetic wave is going to penetrate material, and the depth at which it will penetrate just depends upon the wavelength. And if you're a 5-year-old, you have a tinier head. And so the distance that it penetrates is further into your head than if you're an adult. That's why that picture. This is actually taken from a research paper talking about that specific thing. Anyway, people do sell things that you can put on your cell phone that will protect you from the harmful electromagnetic waves. Is there. And here's my favorite thing about this. You can get the waveguard, which protects you against the electromagnetic waves, with the antenna booster in a packet together, which is delightful. And so the fact that you get one which protects you from the electromagnetic waves and one that boosts them in the same package, I just find that delicious. Anyway, moving on. We can do a quick calculation. When you're talking on the phone, here's a typical power that's emitted by your cell phone. And if you're talking about like at your distance of 5 centimeters from the antenna, so here's the antenna, if you're like some distance inside your noggin, say, let's compute for that power, for that frequency, what is the intensity, what is the electric field strength, and what is the photon energy in electron volts at that distance. And that will help us evaluate how big a deal is this. What I want you to do is I want you to pause the video. I want you to look back through the slides and find the relevant relationships that you need to make these calculations. And then I want you to do them. So I want you to pause right here, and I want you to complete those calculations. I'll be back. Now, the next thing we're going to do before I look at the solutions is talk about how you would do it. We're assuming that the antenna of the cell phone is like a point source antenna. It's like a point source of electromagnetic waves. And we've seen if I have a point source of radiation, the intensity is the power of the source divided by 4 pi r squared, where r is the distance from the source. So I can use that to calculate the intensity. Once I have the intensity, I can calculate the electric field strength. The electric field strength is related to the intensity, and we saw that relationship last time. The photon energy, I can just calculate using the frequency, or I could just use, if I wanted to, I can just use my basic relationship here. I could do like E is equal to the 1240 divided by the wavelength. I could do that piece. And if I took my frequency and converted it into wavelength, but it might be easier just to say E is equal to h times f. And I'm going to use the version of Planck's constant in electron volts. That's 4.14 times 10 to the negative 15th electron volts times seconds. And if I take that number and I multiply it by a frequency, which is in hertz, but hertz is 1 over seconds, so it's times 1.9 times 10 to the 9th, because giga is 10 to the 9th hertz, but hertz is 1 over seconds. The units of seconds cancel, and I'm just left with an energy in electron volts. Putting those pieces together and calculating, I get an intensity of 19 watts per square meter. Now compare that to the intensity. Microwave oven was 5,000 watts per square meter. So that's a significantly smaller intensity. And the intensity will produce a certain amount of heating, but given the intensity is so much less, not so much. Think about this. If I have a square meter of surface area, so a region 1 meter on a side, okay, the amount of energy received is just 19 watts. Well, that's very, very small. If you go outside in the sunlight, the amount of energy this square receives is about 1,000 watts. And so it's significantly less than having the sun shine on you. So that does not seem worrying. The electric field, 120 volts per meter. Well, it takes a couple thousand volts per meter to be able to like ionize gases and fluorescent light bulbs. So this seems small enough to be not super worrying. Also, we can compare that to the Earth's electric field, which is something like 100 volts per meter. And so electric fields like that are not large enough to make a lot of things happen. So I'm not too worried about that. And the photon energy, 7.9 micro electron volts, well, it takes about 1/4 of an electron volt to be able to break a hydrogen bond. So I'm not particularly worried about that. So my sense is talking on the phone is not particularly dangerous. If you're worried about exposure, you can use an earpiece. There's ways to keep your phone away from your head, and there's no downside in doing that. And so you might as well, if you're at all worried, because it could be there's something happening that's sort of subtle and has an electric field that varies at this particular frequency is problematic. But anyway, the quick calculation of the numbers says, I don't see anything immediately worth being super. Biological effects are comparable to shining sunlight on something. It's just basically going to warm it up and about. But check this out. There is data that shows if you talk on the phone, it warms up your face. I mean, check it out. Here's a person in a thermal image. After 1 minute on the phone, you can see there's a little bit of warmth showing up here. After 15 minutes on the phone, there's a big warm area right there on her cheek. And so it's basically because the phone was emitting electromagnetic waves, and is emitting electromagnetic wave, it's warming up that tissue. And so it's not unreasonable. I mean, we can see biological effects. I warm it up at a certain depth, but it doesn't seem, I say, a priori. Now, I want to do some calculations with photons. And here's the first one we'll do. A copepod emits this many photons at a wavelength of 490 nanometers. And the flash lasts for 2.4 seconds. And a copepod is this little crustacean, lives in the deep ocean, and emits a flash of light. And it's doing it to communicate. And as we'll see, it's pretty energetically expensive to send out this flash of light. So whatever it's saying, it better be pretty important. Here's our calculations. First off, what is the energy in the flash? Second is, how many molecules of ATP were required to create it? And then third, what is the power of the flash? Now what I want you to do is I want you to pause the video. I want you to work through these calculations. I want you to reach out to friends. I want you to reach out to learning assistants. I want you to reach out to me to help you figure out how to do these calculations just like you would if you were in class. This online instruction is only going to work if you do the work, if you work through the problems just as you would if we were in class. We need you to practice your skills. So take a couple minutes, pause the video, reach out to people, figure out how to do this calculation, and I'll be back. Now let's talk about how we're going to solve this problem. First off, let's just compute the photon energy. And actually that's kind of a good first step on lots of problems, as we'll see. And we can do that by using our short form, 1240 electron volts divided by 490 nanometers is going to give us the energy of the photon in electron volts. And if we do that, we get an energy of 2.53 electron volts. Now, before I go on, I'm going to start thinking about the molecules of ATP that it's going to take to create that flash. Okay? So let's think about this. When you make each photon, you make each photon one at a time. Well, if I take the energy per photon, which is 2.53 electron volts, and I divide it by the energy per ATP, which is 0.32 electron volts, I get 7.9. But you can't expend 7.9 molecules of ATP. You have to expend 8 molecules of ATP, and maybe 9, depending on if there's efficiencies. The minimum you could possibly get away with would be 8. Okay, so we're going to assume it's 8. So then what you're going to do is you're going to take the energy in the flash is just equal to the energy of the individual photons multiplied by the number of photons. The molecules of ATP, I'm going to take 8 molecules of ATP, which is how much it takes to make one photon, times number of photons. And then for the power of the flash, I'm going to take the energy per photon, and I'm going to convert it to joules. And if I take the energy and convert it to joules, I can just compute the power. It's just equal to delta E over delta T. So I have the energy of the flash in joules. I can just use my basic power equation to calculate it. But the crux of the biscuit, and the thing I want you to remember, is this piece right here. This is an important piece about photons. You make photons one at a time, and you use ATPs one at a time. So 7.9 times the energy in 1 ATP gives me the energy of the photon, but I can't spend 7.9 ATPs. I have to spend 8. And so this particular step is crucial, and make sure you've figured out why that's important. That sort of thing is going to show up frequently in future problems. So here's the relationships that we use, and here's the answers that I get. The energy of a photon, 2.53 electron volts. It's going to take me 8 ATPs to make each photon. So it's going to take me this many ATPs to make the flash. The energy of each photon, if I put it in joules, is this. So this is the energy of the flash in joules. And so the power is just equal to the energy in joules divided by the time in seconds, 2.4 nanowatts. Now that's a very, very small amount of power, so you don't expect to be able to see this at a great distance. But it's energetically pretty expensive. 1.1 times 10 to the 11th ATPs. That's like 100 billion ATPs. So whatever the Copy-Pot is saying, it's important. Now, I want to talk about ionizing radiation, and this is the stuff that people are worried about. And when they see the word radiation, this is the thing they're worried about. They're worried about ultraviolet and other wavelengths where the photon energy is high enough that can actually cause bonds to break, and you can kind of like make things happen at an atomic scale. I want you to do a quick calculation. Here is an ultraviolet lamp that is used for disinfection. Here is one that is used in a tanning bed. Okay? Now, the difference is they're both wavelengths that are emitted by mercury, but there's filters in the glass that only let certain wavelengths through. The germicidal lamps are emitting wavelengths of 254 nanometers, tanning beds 365. What is the energy of each of these in electron volts? Take a second, do the calculation, and then we'll compare. And what I see is this: the energy, a photon energy of the germicidal lamps, 4.9 electron volts. For the tanning bed, 3.4 electron volts. The threshold for damaging DNA is 4.3 electron volts. If a photon has more energy than that, it can bust up a DNA. If it has less energy than that, it can't. And so you can see the photons of this germicidal lamp are above that threshold. They can damage DNA. They will kill things. They will kill cells. For a tanning bed, it's less than that. It's still able to cause certain damage. It's still able to cause certain damage, but it's certainly much, much, much less damaging than these because of the threshold that we have right here. And this idea of the threshold is an important part of the photon picture. As you saw in the little video I made in the studio, blue light and ultraviolet light can do things that red light or green light can't. And it's all about, do the photons have sufficient energy to make those things happen? Now, if you're going to be out someplace where there's ultraviolet, you want to wear sunscreen. And what sunscreen does is it basically just blocks ultraviolet. It absorbs it. The energy of the photons of ultraviolet light are kind of like high enough that they can excite the molecules in sunscreen. They'll absorb it. And so when you put on sunscreen, if you look at the view in ultraviolet, it's a little bit different than it is in visible light. Take a second at some point and take a look at the video we've posted that shows that. Now, I want to continue talking about ionizing radiation. This picture is inside a nuclear reactor, and down inside this pool of water, there are cores. They're the cores where the nuclear reactions are taking place, and they're emitting beta particles and gamma rays, these ionizing radiation. And actually, you can see it's making this kind of like crazy glow here. That kind of stuff, radiation that has enough energy to do stuff like that. That's what. Now let's look at how you would create X-rays, which are a form of high energy ionizing radiation. And the way you do it is like this. I'm going to take electrons, going to boil them off this cathode, put them between two electrodes where they'll accelerate, and the potential difference to make them accelerate is provided by a high voltage power supply. And then each electron is going to strike the target, and each electron will produce one X-ray. So one electron loses kinetic energy and gives energy to a single photon, in this case, an X-ray. So here's a question. If the electron is accelerated through a 5 kilovolt potential difference, what's the maximum photon energy of the resulting X-ray? And second, what's the wavelength? I want you to pause the video. I want you to do a calculation. I want you to reach out to me, to the learning assistants, to your fellow students. Take a minute to do the calculation. I'll be back. Now, if the electron accelerates through a 5 kilovolt potential difference, okay, its kinetic energy is going to increase by 5.0 electron volts. So that's going to be the kinetic energy of the electron. The kinetic energy of the electron is 5.0 electron volts. Now, it's going to give its energy to one photon. And if it gives all the energy that it can, it gives 100% of its kinetic energy to the photon. The maximum possible photon energy, therefore, is just 5.0 electron volts. Now, the electron could give less of its energy to the photon, but it can't give more. So that's the maximum possible photon energy. And then we can just calculate the wavelength, and we calculate the wavelength by just using our basic relationship that the wavelength is equal to 1240. I'm sorry, we take our basic relationship and we rewrite it. The wavelength in nanometers is going to be equal to 1240 divided by the photon energy in electron volts. So I can calculate the wavelength, and it turns out the wavelength's pretty short. The numbers I get for this calculation are this. The energy, of course, of the electron, 5 kiloelectron volts, and so that's the maximum photon energy we can have. The wavelength comes out to be 0.25 nanometers, and that's getting to be on the size of an individual atom. And so the X-ray photons pretty much, they're produced, one electron produces one photon. One photon is going to interact with a single atom. And what it's going to do, it's got enough energy to rip off a significant number of electrons, and so it's going to ionize atoms in a sample. And that's where the problem is. It's going to ionize atoms, it's going to break bonds, it's got 5,000 electron volts, it's got enough energy to do some damage, and it will. Now, as soon as people discovered X-rays, they discovered you could do something amazing with them. You could take the X-rays and use them to produce an image of the inside of someone's hand, because the absorption of X-rays is strongly related of bones. Here's a picture of someone's bone. There's a little bit of metal here. As people figured out you could do that to the atomic image. A picture of my hand that was taken when I damaged it, and they were looking for breaks. And you can see you get a shadow of the mineralized parts of my hand. You don't get much of a shadow of the soft tissue, but you get lots of shadow of the bones. And that made X-ray incredibly useful, and it started taking X number of the things which are in its way. So X-rays pass easily through soft tissue, so they pass through your head. But if there's a chunk of something inside your head which has higher atomic number, it will be strongly absorbed. And so you can make images of metal. But in the early days, people weren't worried about the safety concerns. Check this out. Here's a picture from the physics labs at CSU in 1908, and I found this in a picture of a person in a physics lab class. And the person in the physics lab class is putting his hand on this tube right here. And actually, this tube exists in a case near my office. What's happening is there's a big Wimshurst machine here that's accelerating charged particles. It's making a really, really high potential difference. You're accelerating electrons down the tube, and they're striking this target and giving off ridiculous quantities of X-rays. There's a student who has put his hand right here, and the professor is looking at an X-ray, a real-time X-ray of his hand using this scope. There's a fluorescent screen here, and where the X-rays don't strike it, you're going to have dark spots on the screen. Where they do, you'll have light spots. And so we're going to basically be seeing an X-ray of the person's hand. Meanwhile, this thing is emitting X-rays in all directions. Everybody is getting radiated. People didn't used to be worried about this ionizing radiation. In fact, they were excited by it. If you look at the first Frankenstein movie student center, and look at what brought Frankenstein's monster to life. It wasn't electricity. The electricity was a means to an end. The electricity was a way to make electromagnetic waves. You get electrons moving quickly, and they make high energy electromagnetic waves. And if you look at the movie and you look at what Dr. Frankenstein says, he says something like this: Dr. Wallman, I learned a great deal from you in the university. I learned about the violet ray, the ultraviolet ray, which you said was the highest ray in the spectrum, but you were wrong. I have gone beyond that to create that first great ray which gave life to Earth. So anyway, what he was doing was using his machine with all the sparks and things like that to produce X-rays. What brought Frankenstein's monster to life? X-rays, electromagnetic waves. So people weren't just not scared of them. They were intrigued by them, thought they were kind of awesome. Now we know they are awesome. They are awesome. You should think twice about your exposure to them. They're amazing, but you want to pay some attention. Now, this topic of X-rays and high-energy electromagnetic waves leads naturally into our next topic, which is quantum mechanics or quantum physics. We're going to talk about that next week. And it is one of my favorite topics of the whole course, because we're going to talk about stuff that looks like science fiction, like beaming somebody like they do on Star Trek. Is that possible? That is something we'll talk about when we come back next.